This conference will now be recorded.
Good morning and welcome to this edition of Mirabilis Design's webinar on detecting deadlocks in electronic systems using discrete event simulations. I'm your host, Deepak Shankar, and I'm the founder of Mirabilis Design. And today I'm going to walk you through the methodology, process, and the current generation of capabilities that enables you to be able to assemble task graphs and analyze task graphs for errors or bottlenecks or deadlocks that might be caused by a variety of interactive reasons within a particular design. Before we get started, everybody is placed on mute as we get started, but there is a control panel on the right-hand side of your screen. And if you open up that control panel, you will notice a chat window. Feel free to type in your questions, and we will answer them along way while we're doing the presentation. With this, I would like to get started and welcome you again to this webinar on detecting deadlocks in electronic systems using time-based simulation. A little follow through on the agenda. What we're going to cover today is show you how models are created for task graphs. Most models today that you might have noticed on task graphs are centered around creating either documentation or doing a static analysis on the graph itself. Today, our focus is going to be comparing a static deadlock versus a time-based analysis. So we're going to be analyzing how you can identify deadlocks more as a transition over time because of changes that may occur over time or resources unavailable over time as a result of earlier resources consuming the request, things such as those. We'll also give you an introduction to the state-of-the-art in functional analysis today and a look into VisualSim technology that allows you to be able to assemble models of task graphs and do analysis on them. We're also going to cover the types of analysis, and an important piece of our presentation today is going to cover a list of failures that you could evaluate or you could analyze using the task graph model that you construct. This is important because the failures constitute possible error conditions that may not be easily accessible or constructed either by using a prototype or even by using implementation mechanisms like a C++ code, RTL, or things like that. Before we get started, I'm just going to go through a few definitions on some of the common terms that we're going to be using during this webinar. Everything around the task graph is really about proving the architecture of your system. It can be that you want to more evaluate an architecture that already exists, like a verification type process, or you're looking at a functional specification and you want to optimize it before you give a proposal to your overall design team or to the management or to customers. Some of the specifications that you want to evaluate at this level is really trying to understand what is the flow path, meaning for a particular task or a particular user or a particular service, what is the sequence of events or nodes or processes that occur through the system and the resource consumption of each individual entity. Some of the requirements that have to be met could be timing deadlines, throughput, efficiency, or things where minimization of starvation of services or minimization of starvation of resources. How do we get to this architecture analysis or get to this optimization of the functional requirements? Starts off by really 4 parts, which is functional, performance, power, and failures. Remember, I talked a little bit about failures in the previous slide. Functional analysis is really looking from sensor to attenuator. As any task goes through a sequence of events, you want to look at, what is the arbitration, what's the resource allocation, and the deadlock detection. Now, A lot of the functional correctness, as I mentioned, is tied to timing. That's one of the reasons why when you look at the analysis, you also look at the performance related. So what can performance relation be? Could be things like, if you have different types of queues over time, looking at the sizing of these buffers, looking at the utilization of throughputs, or the efficiency of the throughputs, where you have way too many resources and not enough task flows that are going to be running on top of the resources. And of course, now that you can go anywhere from data centers to edge devices and anything in between, power becomes an issue either from an operational or from reliability standpoint, where you want to have a more effective battery life. Now, to be able to test the overall system and be able to get a coverage, you want to be able to do a widespread error generation or widespread error detection. So we're going to go through the process of how you detect these errors. For those of you that are just joining in, remember that there is a control panel on the right-hand side, and you can keep asking questions as we go along through the presentation. Now, let's take an application task graph. Now, notice here, when we see a task graph, we don't generally specify how the implementation is, because the task graph is simply telling you what are the different nodes or processes and the interaction between these different processes. So the implementation can be either in hardware or in software or in a combination. So for example, over here on the left-hand side, you can see that the auto concurrency is, as you can see, is limited to 3 in each of these, which means there can only be 3 outstanding items executing in each one of these stages or processes, A, B, and C. Now, the words can be interchanged in terms of process, nodes, actors, and there's a few more terms that they use, or even states that people may use for each one of these. And then there could be transitions that are described as between the states. So now when I take something that looks like this and I break it up, or I explode it, what you get is a synchronous data flow graph, which looks like this. So you have a request come in, goes into A1, A2, A3. Now each one of these has multiple outputs, and those fire the next stage, in this case B1 and B2, which again has a data outputs that fire C. Now, some of the requirements are that, as we said, auto concurrency, which is there can only be 3 outstanding activities going on in each one of these elements. Now, what we also have is, from the graph here, you can see that we generate 2 outputs, but then this one here needs 3 inputs. Similarly, this gets a single output, while this one gets 2 inputs. So what we have is a task graph that we had a very, very strict and secure graph, which has now been exploded into this synchronous data flow system right over here. Now, the key thing to look at today is there's a lot of mechanisms that you can use either visually or textually or graphically to go over what would happen in each one of these scenarios to create a bottleneck or to create a deadlock. One of the challenges that is faced with this type of architecture is the bottleneck may not happen immediately. The bottleneck may happen sometime in the future as a result of, say, too many refreshes on my memory controller, on my DRAM, that might cause some of the resource requests for memory to get delayed, and as a result of which the processing gets delayed, and as a result of which the credit going back to the earlier stages also gets delayed, and then you have buffering that slows down your entire system. Now, let's look at a model, a discrete event model built in VisualSim Architect, and see how the model is constructed. So what you see over here is, earlier on, notice there was no traffic, meaning that there was no stimulus to the model. You were just analyzing a sequence of events that occurred within the model, but there's no change in time, or the amount of data coming in is not a variable. With a discrete event model, we've created a variable where we do have traffic that first enters a queue, And if there is sufficient, remember we talked about the number 3, the sufficient autocurrency of 3, then we let the data go flow through. Now, there's also a concept of concurrent execution versus sequential execution. Here what's happening is sequential. So finishes A1, A2, and A3. Each one of these generates this data, which gets becomes a trigger input for B1, B2, and which gets triggered onto C1. So what we're seeing over here is a series of queues, some execution, some sort of a fork and join type operation, traffic, and of course the discrete event simulator itself. Now, what are the types of exploration? Now, before I get into the types of exploration, we're going to walk through the model to try to understand how these models are created very quickly. Now, here what we have is a traffic can be based on a distribution. So this is what we're seeing here, where we're sending something every half a microsecond. Of course, this can be made a variable. And the queues, of course, have some of the basic information, such as a FIFO or the number of queues. In this case, the buffer length is about 100. It's a fairly large queue. Associated with each one of these, in this particular model, we have processing delays. And this is the amount of processing time that it takes. Now, notice that this initial graph does not have any other resources like a memory access or things like that, which, if I take a model that's far more detailed, I'm going to just assemble a model that's far more detailed, you will see additional types of information, such as the memory capacity or the memory usage right over here. Now, what I'm going to do is, before I go into details of the block diagram, I'm going to go ahead and run a simulation just to show you some of the attributes of the design that we're looking at. So when we run the simulation, we're going to see a sequence of events that happen through the system. What I'm going to do here is I'm going to animate the execution so you can actually see what is going through the design. So we're going to notice, so you can actually see that the buffer comes through, and then it goes through these sequence of events. And notice more and more of them are getting collected right here at the A1, which means that probably the queue is starting to build up, because you can see this, like it's built up, but there's nothing moving through, and these take much longer to go through. So what I'm going to do is I'm going to turn off the animation, and we're going to look at the results here. So one of the first things that becomes obvious is that the input buffer occupancy is really increasing linearly, which is not a good sign to indicate that the system has been highly optimized for the resource execution, or even maybe the resource scheduling. Now, one of the things we can also look at here is it shows you the time, the task trace tells me this was A2, A3, and A3. So this is the second output, or the third output that's being fed into B2, and tells me the timestamp as to when each of these events occurred. Now, when I look at this one, you can see this is B1, B2 that's feeding into C1 over here. Tells you what time it arrived at C1. So using this, I can start determining at what time I'm getting each one of these tasks, and then work my way backwards to try to understand where my bottlenecks are. So now going back to the model, what I'm going to do is I'm going to change some of the processing here and make this a little bit faster. So for now, I'm just going to put a few numbers here, and then I'm going to just do the B1 over here and change that to a little bit faster. I'm going to go ahead and rerun the simulation. And you can see, just by doing one part of the system where I speed it up, I didn't speed up the whole system, just a part of the system. Notice my buffer went away. So now, my buffering went away. Now I'm going to get a little more ambitious and say, you know what, this one can be a slightly slower resource. Notice here, we're not specifying that we're using an Intel x86 or we're using an ARM A72 or any of those things. Rather, we're just seeing the resource consumption. Going to do the same thing. We saw that, okay, so now we changed this one, put it back in the old numbers. We put this back in the old numbers. We took this and put it back in the old numbers. Oh no, we made this one a little faster and this one a little faster. So I'm going to go back and make this a little slower and see if this is still an issue. So notice here, the moment I slowed down this A1, immediately I got my bottleneck. Now let me try A2 and try to slow that one down. So processing delay tells me, like how fast my resource is. When I slowed both of those down, I got back to my original conditions. So these lower level and the C are not really the bottleneck. It's the A1 and B1 that are causing the bottleneck, and as a result of which a deadlock was being created. Resource was not being consumed. So now, using this, I can analyze what my system is performing in my in this particular time-based analysis. So looking at the design, a few things occur. One of them is that we can look at the task flow, understanding what happens from source to destination, like we just saw from the traffic generator to C1. And as we saw, we could see what the latencies were and what happens at each point. And then you can see the utilization of resources. Right now, this particular design, we're more interested only in the task graph, so we don't have resources. We look at the usage, but we're going to look at that in the follow-on designs as well. Now, another thing that we can do is really looking at the loading. So what is the memory usage or throughput, and same thing with the bus and switches. What happens if there is a failure or loss of data, non-availability of resources and memory, and also starting look at these task flows where we looked at the top level. We can go look at each one of them. So it looks at number of accesses per node, how many times were the nodes accessed, and whether the nodes were correctly accessed, meaning they came in at the right sequence, and to see if any of them missed their timing deadline. As I mentioned earlier, the buffering is very important in this architecture, because if you noticed here, we saw the buffering increasing, and that's the first clue to say we had to change the resource timing on some of the designs. The other one is looking at scheduler efficiency, which we'll be looking a little bit later when we start putting together a more detailed task graph with more resources and things like that. Now, we looked at the plotting right here, and we looked at the tracing of what was going through the system. So you can actually see both of these kind of outputs from a functional model. Now, we looked at a very small subset or a very small flow right there. Now, what we're doing is we're taking the same thing and putting it in a whole system application. In this case, it's a braking system. And what we're looking at is we've got a set of wheels, we've got the 4 wheels, and we've got a bunch of sensors. Some of them are road condition sensors, proximity sensors, the manual braking by user, things like that. And of course, you have the engine ECU right over here. Now, what we're trying to do with this particular design is that we're looking at the bus, at the brake latency and the speed at which the vehicle is running. The main idea is that the wheels and the engine and the gyro keep feeding in the information to the ECU, and based on the proximity sensor to what is happening around the vehicle, we would either speed up the vehicle or slow down the vehicle. Now, outside of this automated autonomous driving process, there's also the braking, and this would be a manual intervention by the user. Now, what we have as a design is where we, based on the road condition, the acceleration and deceleration would change. And we're looking at cases here, for example, where we had a gravel road, but then the sensor sent in the wrong data, which was related to asphalt. It could be that the data was delayed, or it was the data itself was incorrect. And as a result of this, we ended up accelerating the vehicle, which is we started maintaining a high speed. Now, another option is where we were looking at only the proximity sensor, which had higher priority, and the manual braking had lower priority. And here, while the user was trying to brake, we ended up trying to maintain a high speed at this time. So using this kind of a table, we can actually see what happens when there are errors that are occurring, either as, in this case, either as the way the software is set up, where the proximity sensor had a higher priority over the braking, or where the sensor data itself is incorrect. So you can get a variety of these kind of errors, and then look as a result of which you can see there's a buildup of latency, And notice where there should have been a slowdown, we're seeing an acceleration. So here's where we had an acceleration, which is, while we were braking, versus this is where, the proximity sensor was detecting some vehicle close to us, and as a result of it, the vehicle was slowed down. Now, one of the things to look at functional safety is to be really looking at how does functional safety play a role in my design, and also what are the aspects that have an impact on functional safety. And what we've seen is deadlock analysis is probably the first state of functional safety, where we're really looking at the architecture of the platform and using simulation analysis to be able to come up with the overall, kind of give it an overall safety metric or a safety number. So you can test, as we just saw earlier, for different requirements, which is, proximity sensor versus manual braking versus induced errors or faults, which was the road condition coming in as an incorrect value. And then seeing how the system was reacting to those kind of processes. So kind of walks you through the process that is adopted to be able to not just detect the deadlock, but also resolve it. A quick introduction to Mirabilis Design. Mirabilis Design has been around for many years, and we have been involved in providing support for a variety of projects in architecture exploration through our product VisualSim. VisualSim is our modeling and simulation software, and what we end up providing you is a large library of IP models. And what makes these IP models unique is that there is timing and power embedded in them. And the reason that that becomes important is because rather than the user having to build separate purely functional and purely architecture models, can reuse the same model for both the purposes. Now, as a result of our large number of years of experience, we've actually used VisualSim on a variety of projects. So we had anything from x86 all the way down to an autonomous driving to even to a large-scale industrial copier system and anything in between. Now, the product, as I mentioned, is called VisualSim Architect, and what we have is a platform where you can define your hardware, your software, and networks, and then run a variety of analysis on these particular models. So you can do a variety of Monte Carlo with running a large number of random samples, and then looking at what the statistics that are generated out of the model. The model itself is built graphically, as you saw, and then of course you can do a batch mode simulation to do a large scale analysis by running a variety of statistics or a variety of traffic or use cases as an experiment on that particular design. The whole goal is to really validate and optimize your system even before you go develop it or go build the system. Now, a quick introduction to the library itself. We got an extremely large library that allows you to start at a very abstract, purely functional model, going all the way to a timing or cycle accurate design where you can integrate all your hardware components as well. Also, because of the depth of the library, you can apply the same methodology and the same technology for a variety of applications, going from automotive to defense to semiconductors to multimedia to industrial applications. Now, let's take the functional analysis and look at a flow diagram as to how we do the studies or how we do the experimentation right over here. The way we do it is that you create this model, right? And then you start collecting data when the model gets triggered or executes. So you're generating the flow based on the hardware and software application behavior. And then you run it, in this particular case, we saw the automotive, you run it through the system and then see what the behavior is. This is where we saw the proximity sensor versus the manual braking. Now, what you do is you take the task graph and you map it against a series of execution units. So you map each of the nodes, the processes against these different execution units, and then you run the simulation, determine how much of the resource requirements are there, and then you run a failure analysis. The failure analysis in this case was where we were sending incorrect value for the road condition. On top of this, once you have it, you have the analysis where you determine that, or you identify that there was an error because you saw that the road condition was icy, but it showed asphalt. So you were still running at a high speed, which could cause an injury, or it could even worse cause a major accident. So then you apply the resolution factor to it, and then be able to say, resolve the problem, and that way you have a recovery mechanism, and you get your car to be driving normally in this particular case. So this is kind of the flow diagram in terms of how the functional analysis gets performed in a discrete event environment. Now, here what we're doing is looking at a series of failures. There can be failures coming out of a variety of spaces. So it can be from where I have many tasks, and some of them I get access to as tasks, and some of them I'm waiting for the resources. So if you look at my task graph right down here, I can see where some of them have initial node failures, others have connectivity failures, some of these have dependency failures. So you can have a variety of them, but all of them relate to something that is underlying. It can be hardware failures where you lose some processing cores, or processing cores are being utilized for an extended period of time, to software where you're requesting for excessive resources which are not available in your particular resource units. The other one, which is very common, is a network failure where you don't receive your sensor data, or the sensors are not providing the data fast enough, or in worst case, you might even have sensors sending incorrect data. The other part of it is really the deadlines for scheduling. So you have changes in your slots. So like certain tasks end up getting into the wrong slots, or meaning that it's not able to complete its task within that particular time slot. And it rolls over to the next one. So a number of slots later, you find that it's not able to execute, but in reality, the error was that the time slot happened much, much earlier. Now, over all of these is really today, power is a major issue, primarily because in data centers, they're an operational cost. In edge devices, they're the quality or the value proposition for some of those edge computing devices. So if you're, if you lose power, you're going to be slowing down the process as a result of, say, an LDO efficiency, or maybe a lower voltage, because you're trying to conserve your battery power. Or you actually have to limit yourself for a number of resources by, like, say, in a satellite system where you're not facing the sun. As a result of this, the batteries are not getting charged. So it can be a variety of failures. Some of them can be where the total loss, others can be as a result of the state of your environment that you can look at. Now, this one here is a table to doing what we call an FIR, which is failure identity resolution. So you can have things like, for example, one of the cores fails, which means the loading has to be done on the remaining cores. You can have, and then of course, as a result of which you have to change, the way you have to resolve it is you have to change the fair sharing of requests across these the remaining cores. Similarly, your failures that you're not meeting your timing deadline, you need to revisit the tasks that are being loaded into each one of the slots and look at the execution time to see if some of these are taking way too much time, which means you may have to consider moving them over to an accelerator, or you even have to shut down that slot and then restart it after a time, because it could be that there was like a rolling memory request that has been slowing down the entire system. Now, what we're going to do is we saw a task graph, we saw an application task graph in the braking system. Now, what we're going to look at is we're going to evaluate an extremely large design. So in this case, what you have is a series of parameters. You have some buffers, an input buffer and output buffer, which is targeted at this particular section, which is stage F. So you got 8 stages here. You got A, B, C, D, E, F, G, and H. So you got 8 stages, and then you got a termination point at the other end. Now, what we have going over here is, you notice that each one of these has a single message pointer arriving and a single message pointer departing. But in stage D, what you have is you have the stage, which is the message pointers, but then the message coming out of D gets split or into what we call explode into multiple stages or multiple instances in E, which then feed into F and feed into G, which again has an imploding, which is takes all of them, combines them, and sends it out to the H stage. So what you can have is, depending on the service or the user or the type of packet, any one of those combinations, you could have variable number of these instances for each one of these subsystems, which means also that you can have variable amount of memory requests for the input and a memory request for the output. Now what we're going to do is we're going to look at a more detailed model, and we're going to look at how this detailed model was constructed. I'm going to move over to VisualSim. So this is the VisualSim block diagram. As I mentioned before, we have a series of libraries, anything from traffic generators to resources, which can be queues or schedulers or server resources, and to power units like batteries and things such as those, all the way down to hardware and software components like RTOSes and buses and processors and memories and things like that. Now, here what we're seeing is, you can see again the user input that is being triggered, and here we have a logic which is based on the user input. We're going to have a release time, which essentially means that for every user input, there's going to be multiple user types that are going to be generated. So for each one, we're actually generating 7, starting from 1 to 7, and there's like a time delay or scheduling overhead between each one of those. So, so you can essentially think about it as, for every request coming in, I generate multiple of these user types. And then they're going to go through these sequence of things. Now, every one of these, once they come into a node, gets mapped into the scheduler over here. Now, the scheduler itself uses information from some databases, which is right over here, which is the execution time for each one of these nodes is a range of cycle time. And there's a clock speed to tell you what the speed of the thing resources are. Now, this one over here is telling me the number of code blocks in this case per user, which is each of these user types, and tells me the memories and tells me the queue number, which is essentially the number of bits. So depending on the scenario, the number of bits would keep changing. Now, what we also have is a concept of concurrent versus sequential. Remember, we had the exploding and the imploding. So we can either execute them, all of them concurrently, or we can go sequentially, saying instance 1, instance 2, instance 3, and send only after the first one finishes, we send it over to this one over here. Now, I'm going to go ahead and run the system. And we're going to see a variety of statistics come out. This one here we're going to focus on is the trace, which tells me at what times they come in and out of each one of the stages in my particular design. Versus this one over here, which is telling me that this is my threshold or my timing deadline. And you can see this was above the threshold, which means it didn't meet the deadline. And these were below the threshold, they met all the deadlines. So you can see most of the time, everything was good. Everything was below threshold, except that there was a slight buildup over here of request, and boom, you had a few tasks that did not meet the deadline. Similarly here, you notice all of a sudden we had a buildup, and then you had a bunch of tasks that did not meet the deadline. And after that, they kind of slowed down and they ran it through. A static analysis would not have been able to capture this kind of information. which is where the time-based situation comes into play, or time-based analysis comes into play here. Now, one of the key things here is, since we're running more dynamic and we're accessing the different resources, you can now see that we're generating the statistics associated with this particular design. So what we're seeing over here, for example, is the DRAM utilization. Notice they're at like 75% right over here. And then we're looking at the DRAM delay. So what's the average delay through the design? And then how much of memory is used. So in this case, we can see we're at a peak of about 1.5 gigabytes of data that we're actually using in this thing. So you can also see what the effective throughput was, which is actually about 5 gigabytes per second is what my effective throughput is for this particular design at your running. So using this model, you can actually evaluate what is my resource requirements in terms of the memory, in terms of, if my deadlines being met, which means my processing resources are sufficient, but my DRAM resources are probably require extremely fast memories, which can be a DDR5 or greater. So if you look at the specification on this one, you can see it's a DDR4 with a 64-bit interface, and you can see that we're running at 2.4 gigahertz. So it gives you the information that you would need to go in and start putting in more details into the particular architecture. So I can at some point refine this to be able to look at additional elements, such as, for example, over here, I've got a queue, and I can look at what should be the sizing of that particular queue. So what's going to be the buffer depth. Now, what I also have, which I'm not using at this stage, is every one of these components over here, every one of these nodes here, could be assigned as they come in to have a different priority levels. Higher the priority, higher the number, higher the priority. And what this allows you to do is allows you to give preferences for certain elements of the flow, which can cause priority inversion or starving some of the resources that may end up causing a bottleneck. So it allows you to experiment with those kind of elements as well. Now, other parts of the system that you can experiment with is, of course, what is my processing capacity? So the execution time, which, as I mentioned, was right over here. So that's the execution cycles, and then I compute the execution time in one of these components here. I'm sorry. I compute the execution time right in the task behavior section, which is right down here. That's my execution time, which is, it goes and gets the day, it goes and gets the execution cycles, and then it uses the core speed and comes up with, what's going to be the delay here. Now, as I look through the design here, notice it's purely a flow forward. The only place here is I'm going to get local buffer data and I execute here. So if you wonder, wait a minute, all I need to do is just speed it up and I would end up not having a bottleneck. But remember, there's also a limitation on a couple of different things. One is I got a scheduling overhead where I can vary the number of users coming in or vary the number of points based on the input traffic. In this kind of particular case, the packets coming in. But I can also end up having to vary the core speed over here, which would have an impact on my resource usage or my resource consumption. Now here, what I can do is I can change this to to make it more sequential, and then rerun the same design and try to see if there is impact on any of these different devices. So one of the things you notice right over here is that there's a slight modification in my memory usage and in the throughput, not significant, but a slight modification. And but there's really nothing waiting for resources, which means that I have pretty good coverage. So what I'm going to do here is I'm going to actually change the number of resources available. So we have got about 100 resources. Resources, essentially, if you think about an artificial intelligence or GPU or things like that, these would be the number of execution units. So these would be the number of threads that can concurrently be executing. So I'm going to make this like 60. So we're dropping it down by about 40%. I'm going to rerun the system, and then I immediately get an error saying that, hey, I can't handle the traffic anymore because I've got way too many requests coming in. So as a result of that, you notice here that I've gotten this thing where I've got a huge number of packets that are actually waiting to be processed. I can't take can't handle the processing through the particular design. So right immediately when you have an error, it identifies the error and shows you immediately what the problem is with the particular design, and it allows you to identify where your system bottleneck is. So for example, I'm going to change this and make it like 80%, or I'm sorry, 80 resources, to try to see what's going to happen in my system. And notice now that with 80, I'm still able to meet my deadline. So which means that I had 20 extra resources that I did not require. So what I can do is try to get this down a little bit, and so I'm doing some experiments. So this is what you could do at the command line and try out different variations. So you now brought it down to about 70, and notice there's a few more peaks over here which were not there earlier, but I'm still getting the same performance. I'm still getting the same throughput, which means that I can still handle the flows over here. Now, one of the things I can also do, for example, is I could change the rate at which the data is coming in. So this is a network interface, so we've got a Poisson distribution that we're using. But what I can do is I can increase, or I can actually decrease it. So I can make it 0.7. That's my distribution right over here. I'll go ahead and rerun it and then try to see. And again, notice over here, I end up having data waiting for resources, and I end up seeing this where I get a lot more their points or nodes that are not able to meet the deadline, and only a few of them that are meeting the deadline. So there's a variety of variables that I can modify to evaluate how the system actually operates. And as you can see, the behavior flow over here either depends on the traffic, depends on the statistics for each of the nodes, or it depends on each of these individual components, like changing the number of resources, or changing the clock speed, or changing the DRAM type, a variety of these things that could tell me how my nodes are going to be operating in terms of where my deadlines are and things like that, or whether I'm able to meet my deadline or not. Now, going through the design, we talked about a number of components, and I'd like to just take a few minutes just discussing some of these components to help you understand what are these components that you're actually using. First and foremost is a digital simulator, which is a discrete event simulator, which allows you to send events in synchronous time across asynchronous time frames. So you're not sending it like every clock cycle or every 1 hour or things like that, but rather you're sending it at a variable time space. The second part of it is the traffic, and in this case we focused on a Poisson distribution, but it could also be replaced with an input trace that might be from an existing system, or it could be something that's generated from a static analysis tool as well. The other piece of it is, if you notice, we had the task graph, and then we had the architecture or the resources. So the resources can be a variety of things ranging from the memories, but it can also extend to other components like an AI accelerator or a processor or a GPU. But in this particular case, since we're more on the stochastic or a function analysis, we focus more on queues and scheduling and resource and server resources. The task graph itself, as you saw, was a script that was written to describe each of the components. There were some control functions, and then there was the mapping process of sending each of the nodes up to this scheduler that then determined what to do. The other part of it, which was important in the task graph, was really the database that provided you all the statistics and metrics that was required for the task graph nodes to be mapped to the resources. Now, the other side of it is the post-processing, which is all the different types of statistics that you need to generate to be able to make decisions on these task graphs. So it can be looking at the end-to-end latencies. It can be to look at the throughput available. So if I go back to the model again, notice over here, when we run the simulation, this was the task completion time, right? This is really the end-to-end latency from the time that the packet was generated all the way to the time that it hit the finished states stage H. And here it shows you your individual task activity as well. The last part is the visualization. As you can see, there's graphical plotting. There is the animation I showed you, which is, if I go back to the block diagram and I create this animation over here, I'm actually going to increase the resources over here. I'm going to generate animation on this model so I can actually see what's going on. So you can see the sequence of things as it's flowing through the design. So you can see the A's are generating a lot of activity, but then, you know, it's like there's a lot of traffic. So this is generating a lot of this traffic, and then it's, you know, there's the activity over here on the resources, as you can see, and then there is the eventually there's going to be a flow through these other components. So the there you go, you're moving up to B, and then you're going to slowly, like the tasks that are done with A are moving on to B, and then they're going to flow through the system. Now, one of the things is we're trying to bring together function analysis and deadlock detection into a system model. And really the purpose for doing that is because with model-based system analysis, you can combine the requirements and match that against optimization of the specification, and you can test for deadlocks and functional safety here. Now, this webinar itself, we didn't use the terms such as semiconductors or a processing core or a particular type of sensor, but rather we showed how you can integrate all of these into a single stochastic analysis to identify where my deadlocks are in this particular design. So, and as I mentioned, you can import over time as you start adding more and more granularity, import information like this part is in software, this part is in hardware, so you can do a partitioning. You can integrate your semiconductors either as an on-chip type analysis or as a large system, integrate different types of sensor data that could be imported into the design, add your networks. Now, network itself doesn't mean an Ethernet or a 5G or Bluetooth, but rather it can be a network within a chip, or it can be a network within a particular box. So if you have like a data center where you have 300 boards and you have connectivity between the boards, which could just be a high-speed PCI Express, for example, or just a serial interface between all of them. And of course, lastly, the power system, which is probably the most important component that kind of puts everybody together, or puts all of these subsystems together. So with this, I'd like to wrap up the presentation, open it out to questions, and feel free to ask me questions on the chat window, which is on the right side.